So our goal, or our motivating question for all of Chapter 5 is going to be, well, how would I find the area of a geometric figure that looked like this? So when we look at this, it's not a square, it's not a rectangle, it's not a triangle, it's not any of those things, and I can't really divide it into squares, rectangles, triangles, and circles, etc. So the idea then is we could start trying to approximate the area very coarsely for my first approximation by just putting this entire geometric figure inside of a rectangle. So if I did this, I have this rectangle. This rectangle would represent an overestimate of the area of that geometric region, right? Because we're counting a whole bunch of stuff that's not in there. Well, I could revise this and get a better approximation maybe by subdividing it into more rectangles. So for instance, if I were to subdivide it into some rectangles, maybe like this, like this, like this, and like this. If I now just found the area of these red rectangles, that would be a better approximation. And if I kept getting more and more rectangles, I could find a better and better approximation for that area, right? So that's kind of a generalized idea of what we're going to do. So it wouldn't be 100% accurate, but it would be better than that one big rectangle. And then if I made 10 rectangles, that's going to be better than if I did 4. And if I do 100 rectangles, that's going to get more and more accurate. So let's keep this idea in mind as we move forward. So we're going to go back and review a couple of things from college algebra because they are going to be important for what we're trying to do. So let's review sigma notation. So sigma notation, we have our Greek letter, capital sigma, and our Greek letter sigma is our sum operator, and what that means is to add. And so the sum operator is we input a function and it tells us the sum of that function, or as we called it in college algebra, a sequence, and adds up all of the members between two different members. So to remember the anatomy of our sigma operator, we have sigma, and then on the bottom we have a variable, or the index equals a number. On the top we have another number, and then here we're going to have our input. And let's talk about what each of these are. So this is our index and our starting value. And what I mean by starting value is it's really our starting input. So it tells us to start with the first term. The number on top is also an index, but it is our stopping index. That's our stopping input. And then we have a general term of a sequence. And what that really is it's just some function that we're going to input some different values into. So if we take a look at our example, we have our sigma notation. We're indexed on I, and it's I equals 1 to 27 of I. So the first thing is this symbol is read as the sum as I goes from 1 to 27 of I. So the sum is our sigma operator. The sum as I goes from 1, so that's this part, to our stopping value, to 27 of our general term of our sequence or our function, I. And so what this literally means when we have the sum as I goes from 1 to 27 of I, the literal definition of this is it's 1 plus 2 plus 3 plus 4 plus ... plus 25 plus 26 plus 27. So it means we are going to put in our input I equals 1 into I. That gives us our first one. And then I goes to 2, 3, and so forth. So this is our function right here, our a sub I. And it gives us all of these values. So our rule, a sub I, or if you prefer, we can think of it as, we have a sub I equals I, or if you prefer, you can think of it as f of I is equal to I. All right, so let's remind ourselves a couple of things, like how do we do this on our calculator? So in case we don't remember, we can find the sigma notation on our calculator by pressing alpha and then window. And we'll see that sigma is choice number 2 on our calculator. So we could just type this sigma notation in directly. So we're going to have the sum as I goes from 1 to 27 of I. And then that tells us that the sum as I goes from 1 to 27 of I is going to be 378. All right, so the next one is a U-try for you guys. So let's go ahead and calculate the sum as n goes from 1 to 10 of 1/2 raised to the n minus 1. That when inputting something like this into our calculator, we can't use the parentheses that are put in by the sigma notation. So if we grab our sigma, and the question came up in a couple of the different breakouts, does it matter if I use n? And the answer is no, as long as it's consistent. A lot of people just like to type x because it's easier to get. So this, but the thing we have to be careful about is since we have 1/2 to the n minus 1, I have to insert my own parentheses, which oddly enough the calculator is going to take out after we're done, but it'll still process the answer correctly, and we should have gotten 1023 over 512 for our solution. All right, so we'll do a few more things involving sigma notation in our calculator as time goes on. All right, so now we've been talking about how this chapter is going to be all about finding area. So we know from geometry how to find the area of rectangles, parallelograms, triangles, and circles. Well, we want to find the area bounded by general functions. So let's start with the following question and see what we can do. So if we start with, we want to find the area bounded by the curve y equals x squared for x between 0 and 1 in the x-axis. So if we were to draw a graph, we have our parabola, or the part of our parabola between 0 and 1, which is this, and then dropping down to the x-axis, we get this. We want to find the area of this region. And when we look at it, this area is not a triangle, it's not a rectangle, it's not any of those things. So the idea is we're going to go back to what we did in the very beginning. We want to use rectangles to estimate the area underneath the curve. And rectangles have a very simple area formula, which is 1/2 base times height. So like we did at the very, very beginning, I could get a terrible estimate by just putting one rectangle on this and finding the area of that rectangle. Well, that's not a good estimate. Let's see if we can do better. So we've got a couple of graphs. So let's start with this, and we want to find an estimate of this area by using 4 approximating rectangles. So this can happen in 2 different ways. So if I have if I'm going to use 4 different rectangles, let's cut each of these in half. 1, so that's 0.5 and 0.5. And if I cut them in half again, that would be 0.25 and 0.25, 0.25 and 0.25, right? So now I could make some rectangles by going up to the curve and then drawing a rectangle with that height. So I go up to the curve, and then I make a rectangle with that height. I go up to the curve, and I make a rectangle with that height. And I go up to the curve, and I'm going to make a rectangle with that height. So now if I look at these 4 rectangles that I've made, based on that picture, is that going to be an overestimate or an underestimate of the area? Well, it's going to be an overestimate because all of those rectangles are above the curve. So a couple of things we are going to take note of. Well, what is the width or the base of each of these rectangles? Well, each of them have width 1/4, right? This is 1/4, and this is 1/4. So we have 4 rectangles, all with height, or all with base 1/4. Then we're going to have each of these are going to represent the height of each of these rectangles. So the height for this first point is going to be 0.25 and f of 0.25. Then this one, my input was 0.5, is going to be 0.5 and f of 0.5. This guy right here, that should have been 7.5, I had a typo there, is going to be 0.75 and f of 0.75. And then lastly, this is going to be 1 and f of 1. Those would be all those points. So then each of these rectangles has width 1/4. So the area of my first rectangle, if I were to call this A1, A2, A3, and A4, the area of the first rectangle is going to be 1/4 times f of 0.25. The area of our second rectangle is going to be 1/4 times f of 0.5 plus 1/4 times f of 0.75 plus 1/4 times f of 1. And so that's each of my areas, because this is A1 plus A2 plus A3 plus A4. So the first thing we notice is the width of each rectangle is constant at 1/4. So we could factor that out. And then that would just leave behind f of 0.25 plus f of 0.5 plus f of 0.75 plus f of 1. So that would give us an estimate of that error. So let's grab our graphing device and go ahead and put this in. So I have 1/4. Oh, I need to put my function in first. I'm getting ahead of myself. So we go to y equals. Our function was just x squared. And then we would go 1/4. And then we have parenthesis. We need to put in 0.25. So we go alpha trace. And we get y1. And we're going to put in 0.25 plus alpha trace y1, we're going to put in 0.5 plus alpha trace y1, this time we put in 0.75 plus alpha trace to get our y value again, y of 1. And we press enter, and our calculator thinks for a second, and we get, this is a decimal, or if we press math and choose fraction, we get 15 over 32 is our approximation of the area underneath that curve. So in this example, when we did this, we used the right endpoint of each of these to find an estimate for the height all of those, and it turned out that we got an overestimate. Well, I could do the same thing again on this other picture, but what if I use the left point to find my rectangles? Well, then my rectangles would look like this. And if my rectangles look like this, so then this is A1, A2, A3, and A4. In my green approximation, I would have an underestimate because all of my approximating rectangles lie below the curve. Once again, we'll notice the width of each rectangle is still 1/4, but now the heights are given by f of 0. The height here is f of 0.25. The height here is f of 0.5, and the height here is going to be f of 0.75. And this first rectangle is interesting because f of 0 is going to be 0. So that first rectangle actually has height 0. And it's not really contributing anything to the value or the area underneath the curve. So writing this out, I would have 1/4 times f of 0 plus f of 0.25 plus f of 0.5 plus f of 0.75, closing our parentheses. And if I put this into the calculator, I'm going to have 1/4 times y of 0 plus y of 0.25 plus y of 0.5 plus, that was not the right button, y of 0.75. Close our parentheses, and this time we get 0.21875, and if I turn that into a fraction, I get 7/32. That is also not what I wanted. All right, there we go. So then the picture on the left was an overestimate, and the picture on the right is an underestimate, and we're trying to find the area. So based on that, we know that the area has to be less than or equal to 15/32, but it also has to be greater than or equal to 7/32. So based on this, we could improve our approximation by averaging the overestimate and the underestimate. So we could improve by averaging the over and underestimate. So we would get that the area would be approximately equal to 7/32 plus 15/32, and then we average it over 2. So 7 and 15 give us 22/32. Turning that into 2/1, we multiply by the reciprocal, and that would give us 11/32 for an approximation. Okay, so based on what we just saw, we found an approximation of the area underneath this curve, and we did it by using an upper estimate and a lower estimate. So to get the lower estimate, we use the left endpoints in this case, and in the upper estimate, we use the right endpoints. All right, so we need to practice doing these, and the best way to do so is for us to do a U-try. So it's now your turn. So we're going to work pretty much the same problem, but this time, instead of using 4 approximating rectangles, you've been asked to find an upper and lower estimate for the same graph, but this time we want to use 8 approximating rectangles. All right, well, let's go ahead and take a look at our U-try. So we want to try to make this as efficient as possible, and we're trying to use n equals 8 approximating rectangles for the values between 0 and 1, right? So if we wanted to, well, we know we need to subdivide this into 8 equal parts. So there's a half, there's our quarters, and then we would have our eighths. So that's 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 1 is the same as 8/8, and 0, if we need it, is the same as 0/8, right? So to find our overestimate and our underestimate, we're going to be using either 0 to 7/8 for our underestimate, or 1/8 to 1 to find our overestimate. So it turns out we can find a sequence that represents this. In fact, what we're seeing here, if we look at all of these as different inputs, so if I were to pair this with, make a table of values, and think of this as a sequence n and a sub n, we would have 0 pairs with 0, 1 pairs with 1/8, 2 pairs with 2/8, 3 pairs with 3/8, 4 pairs with 4/8, 5 pairs with 5/8, and so forth, 6 with 6/8, 7 with 7/8, and 8 pairs with 8/8. So in terms of a sequence, it looks like our denominator always stays constant at 8, and our numerator is increasing by 1 every time, so it's going to be n. And if we checked that, if I put in n equals 0, 0 divided by 8 gives us 0. If I put in n equals 1, 1 over 8 gives us 1, and so forth. For all of these different things, the other thing we could note is that this is really just a linear function. If you find its slope, the slope is 1/8, and then this is just that linear equation. If we want to think of it that way, it is f of n equals 1/8 times n, and either way is a valid way to think of that representation. Well then, this gives us each of the inputs on our graph. So these are like our inputs. So it's probably a better idea not to think of it this way, because this will, it might confuse our inputs with our outputs. So these are our inputs. And the function that we are trying to approximate the area underneath was our squaring function. So it looks like this, right? So this function is f of x equals x squared. And we know that the width of each of our rectangles is going to be 1/8. And then the height of each rectangle, so this is our base, is going to be 1/8. And then the height is going to be f evaluated at n over 8. And that's going to be our height. So then we need to add all of these up. So for our lower estimate, it would be, we would start at 0 and stop at 7. So that would be the sum as n goes from 0 to 7 of 1/8 times f evaluated at n over 8. And then our overestimate would be the sum, and instead of starting at n equals 0, we would start at n equals 1. And this time we would go to 8, and it's going to be 1/8 times f of n divided by 8. So something we may or may not remember from pre-calculus is that we can actually just pull constants out of sums. So for simplicity, we can just do 1/8 times the sum as n goes from 0 to 7 of f of n over 8. And the same thing here, we pull the 1/8 out in front. The sum as n goes from 1 to 8 of f of n over 8. So let's go ahead and put each of these in our calculator and calculate these sums. So the first thing we need to do is make sure our squaring function is in. So that's our f, and it's already in our calculator. And then we are going to have 1/8. And then we have alpha window. We grab our sum as n goes from 0. So as n goes from 0 to 7 of alpha trace, we grab our function, our y, of alpha y equals, to get our fraction, n divided by 8. And then we close our parentheses and we press enter, and our calculator thinks for a second, and it gives us our lower estimate as being 35 over 128. So I know from talking to you guys that you all got this value, but you wrote it out the long way like I did in the previous example. So I want to take a second. All right, so putting the overestimate into our calculator is going to be almost exactly the same thing. And in fact, I'm going to go press second and enter to pull up what I typed on the previous line. Because in fact, I only have to change two things. So instead of n starting at 0, it's going to start at 1. And instead of stopping at 7, it's going to stop at 8. And when I do that, my calculator gives me the overestimate, and this time that's 51 over 128. So if we wanted a better approximation, we could add those two things together. So plus 35 over 128 and then divide that by 2, and we would get 43 over 128 as an approximation of that area. So we won't calculate it exactly today, we will next time. But it turns out the exact area underneath that curve is 1/3, and we'll see why. So our approximation is accurate to 2 decimal places, which isn't too bad considering we only used 8 rectangles to approximate this. So as you might have guessed, when we did 4 rectangles, we got an okay approximation. When we did 8 rectangles, it got better. Well, if I did 100 rectangles, it's going to get much better. So how would this change if I wanted to use 100 rectangles? Well, in this first one, it was 1 over the number of rectangles. So let's try it with 100, would be 100. And then my sum would go from n equals 0 to 99 of f of n over 100. And for the overestimate, instead of going from 0 to 99, it would go from 1 to 100. Well, let's just go ahead and see what this estimate is. We'll also note that our calculator is going to struggle a bit with this. It's going to take it a second to add up all of those things. So 1 over 100, sigma, not sigma, let's try that again. 1 over 100, sigma as n goes from 0 to 99 of y of n divided by 100. All right, so as we've observed, the more rectangles we use, the better and better our approximation is going to get. So the idea of example number 2 is we want to combine the idea that we were just doing with limits. Because in calculus, we know we can take the limit as n goes to different places. So specifically, since we know that the more rectangles we use, the better the approximation gets, why don't we try this? So if we let the number of rectangles, if we let n go to infinity, then the error in our approximation would have to go to 0. So just to give you a second to let this sink in, our goal now is, instead of using 4 rectangles, 8 rectangles, or 100 rectangles, is, well, what if we put an infinite number of rectangles under the curve and add all of those up? And then, if we can do that, if we can add up this infinite number of rectangles, it's going to give us the exact error. So there's going to, or the exact area with 0 error underneath the curve. All right, so we're going to be working on this for the next little bit, but let's go ahead and draw a picture, or draw on this picture, and see what we get. So I want a bigger graph, so I'm going to recut this. So our idea is to do the same thing that we just did, but now we want to do it here. So we want to go all the way to 1, and I'm going to write 1 as n divided by n. We're going to start at 0, which is going to be 0 over n. And then we're going to subdivide this into n equal parts. So that's going to be 1 over n, 2 over n, dot, 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 till I get out here, n minus 2 over n minus 1 over n, and then finally n over n gives us 1. So then the width of each rectangle is 1 over n. Right? Because it's 1 over n, 2 over n, 3 over n, 4 over n, all the way out. And then the height of each rectangle is going to be f of 1 over n. In this case, we're not quite. So we've got to be a little bit careful. I'm getting ahead of myself. So we have 1 over n, 2 over n, n over n. So what's happening in the numerator each time in this sequence? So this time, instead of using n's, I'm going to have a sub I is going to be I divided by n. And we're going to note I changes, n is fixed. We divided this into n equal parts, and then I is going to go from either 0 to n minus 1 or from 1 to n to get our lower and our upper estimate. So then this gives us that a sub I is I over n. So then our height of each rectangle is going to be f of I divided by n, which is I divided by n squared. So our height is going to be I squared over n squared. So then that's the area of each approximating rectangle is its base times its height, which we just found each of those. So our base, or our width, is 1 over n. So we get a sub I is equal to 1 over n times I squared over n squared, which is our height. So I squared over n cubed. So then that's the height of each rectangle, but now we need to figure out our area, which is going to be approximately equal to the sum. And remember, I is what's changing and n is fixed. So we're going to take the sum as I goes from 1 to n, because remember, n is the number of rectangles, of I squared over n cubed. And that gives us an approximation of the area. So if we take the limit as n goes to infinity, we will get the exact area. All right, so we're going to put this on the back burner for a second because we want to keep on generalizing. So we did this for a specific function, f of x equals x squared, on a specific interval 0 to 1. Well, we want to generalize this to any function on any interval a comma b, because we're not always going to be working with the squaring function, and we're not always going to be working on the interval from 0 to 1. So let's take this and generalize it to anything. In order to do so, we're going to introduce some new vocabulary, and I'm going to draw a picture to help justify what we're doing. So imagine we have some curve f of x, and we have a, and we have b, and we're trying to find this area underneath the curve between a and b. So the first thing we wish to do is we wish to divide the interval AB into n equal parts. We will call the width of each rectangle delta x. delta x is defined to be b minus a divided by n. So this is the length of the interval So in the previous example that we were doing, the length of the interval was 1. That's all we had, why we always had 1 in the numerator. And n is going to be the number of rectangles. We will create a partition of the interval so we imagine our number line. We start at A and we're going to end at B, and we're going to name each of these. So A is going to be x0. Our next partition is going to be x1, which is A plus delta x. And then our next one, x2, is a plus 2 delta x, all the way out until we get to xn, which is going to be a plus n times delta x, which would add up to b. So then this gives a formula for these x's. So our x sub I is then equal to a plus I times delta x. And as we saw above, it's worth noting, so note that x sub 0 is equal to a plus 0 times delta x, which gives us a, which is the first one, and x sub n is equal to a plus n times delta x. But delta x, by definition, is b minus a over n. So then the n's reduce out, and we're left with a plus b minus a, and the a's add up to 0, and we get b as advertised. So the x sub i's give us our partition, which is it's the x values, or the inputs, that divided up our interval AB into equal parts. In other words, it's the inputs that we're going to use in our sigma notation. So in essence, these are going to be our inputs for f. So the approximation using the right endpoint is denoted as r sub n, and it is going to equal delta x times f of x1 plus f of x2 plus dot 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 f of xn minus 1 plus f of xn, or collapsing that into sigma notation, it is delta x times the sum as n goes from 1, or as I goes from 1 to n. sorry, of f of x sub I. This is called the Riemann sum. Using the right endpoints. The left endpoint sum is, instead of I starting at 1, it starts at 0, and instead of ending at n, it ends at n minus 1. And it's going to be the same thing, delta x times f of x sub I. So the area under the curve, the exact area under the curve, f of x on the interval AB is the limit of the sum of approximating rectangles. So, in other words, the grand conclusion is this: the exact area A is equal to the limit, as n goes to infinity, of the sum, as I goes from 1 to n, of f of x sub I times delta x, which is equal to the limit, as n goes to infinity, of the sum, as I goes from 0 to n minus 1, of f of x sub I delta x. So it says, when we take the limit as n goes to infinity, it doesn't matter if we're using the left Riemann sum or the right Riemann sum. The limit, when the area exists, is going to be the same whether or not we use the left endpoint approximation or the right endpoint approximation. And just to be explicit, this is where x sub I is equal to a plus I delta x, and delta x is equal to b minus a all over n. All right, so that is the formal definition of the Riemann sum. We're going to only, in this section, only be doing the finite approximations. In 5.2, we'll start doing the limits as n goes to infinity. So let's go ahead and take a look at our last example for 5.1. Which is the speed of a car in feet per second is given in the table below in the table below. Estimate the distance traveled in 30 seconds. So we have our input is time and our output is velocity in feet per second. And we want to estimate the distance traveled. So if we think back to derivatives, if we have a position function, The derivative of position is velocity, and then the derivative of velocity is acceleration. So we were given velocity, and we want to estimate the distance traveled. Well, to make a connection, we're going to take a sidebar for a second. If I said you were driving 60 miles an hour for 3 hours, how far did you go? Well, you would just go 60 times 3 gives you 180. Let's draw a picture. So what if I have time on my horizontal axis and I have velocity on my vertical axis? So if I'm driving 60 miles per hour and I do that for 3 hours, well, that's a constant function if I graph it. Well, what would the area of this rectangle be? Well, its width is 3 and its height is 160, so its area is 180. So the area of that rectangle represents the total distance traveled. Turns out, in general, that is true, as we'll talk about more in Chapter 5. But based on that, if we want to estimate our distance traveled when we know velocities, we can use approximating rectangles. So if we do that, this would be t0, t1, t2, t3, t4, t5, and t6. So if we want to estimate the distance traveled, what would be our delta t in this example? Well, our t is going up by 5 every time, so the width of each of our rectangles is going to be 5. So then our left approximation is going to be my delta t times my outputs at the left endpoints. That's going to be 25 plus 31 plus 35 plus 43 plus 47 plus 46 plus, nope, not 41, because I only go to minus 1. And then my right approximation is going to be the same thing, but I don't start at 25. I go 31 plus 35 plus 43 plus 47 plus 46 plus 41. And then if I put each of these into my calculator, I can get my left and my right approximations. So I have 5 times 25 plus 31 plus 35 plus 43 plus 47 plus 46. And that gives me my left approximation. Then I do the same thing, 5 times 31 plus 35 plus 43 plus 47 plus 46 plus 41. And I get 1215. So I get my two different approximations of 1,135 feet and 1,215 feet.